Alright, so small sets, why? Well, it's a necessity. And why is it so? The reason is that otherwise we are going to land up with strange problems strange problems. So let's give an example. So suppose we are writing things like this, and we have, as we agreed, that sets will be completely described by formulas, well-formed formulas. They are the properties. Very good. So I can make up this set. Right? Agreed?
Agreed.
Okay. Now, if this is a set, because I said that sets are going to be given by properties, collection of objects which are satisfy some properties. We agreed that properties are best modeled in terms of well-formed formulae, and this one is obviously a well-formed formulae because x belongs to y is a well-formed formulae. If I put x belongs to x is a well-formed formulae. Negation of x belongs to x, which is this, and that is a well-formed formulae. So now what happens with this? A is going to be a member of A itself if and only if it satisfies this well-formed formulae. That means A is not going to be a member of A. Now this is a strange thing. I have a statement and its negation equivalent. And it can never happen because whenever the statement is true, its negation is false. And equivalence doesn't become true when the two statements are having different truth values. So equivalence, the idea of equivalence means that both of the statements have the same truth value. So what is the problem? Now there are two ways. The immediate problem is, what one suspects is possibly then we shouldn't allow A should not be a set. But you said so, that everything which is described by a formula must be a set. So then what turns out is there are two aspects of this. Well, I call them leftists and rightists. Well, this is just a mnemonic. So you can think of this epsilon as having a kind of a formal symbol which has two sides. One place is taken by square and the other place is taken by. Now the leftists, they restrict this side, and the rightists, they restrict the right hand side. Okay? Now, what do I mean by restrict? That means not everything will sit on the left hand side. So not every set A can belong to and another B. Okay? Now I shall call a set. A is said to be a small set. Or let me change the X is said to be a small set. If there exists a Y such that X belongs to Y. And so this statement is formulated or written formally as by writing X, small xy. Okay? So it means that X is a small set. That means there exists a Y which contains X as one of its elements. And negation, this is a set which is often called a large set, which is cannot be an element. Any. There are other names as for small. The other name for small is, people, when they use this, so I use small set and large set because it seems to be very intuitive. People call large sets proper classes, and this is then just called a set. Okay. Now, so in there, when they use the word proper classes, as I said, everything is a set, they will say everything is a class. And proper classes are what I will call large sets, and sets is what I will call a small set. This is the usual formulation of NBG kind of set theory. N for von Neumann, B for Bernays, and G for Gödel. Now, here, this is the kind of set theory which is called ZF. So, which is Zermelo and Frankel. Yeah. Now, ZF, on the other hand, doesn't allow. So, what happens in ZF, we will see, I'll indicate this as we go down the line. What happens in ZF is these things, these diamonds, so as the sets start to get bigger, suddenly they vanish. They are no more sets. They are just formulae. Okay? So you just work with formulas then. You don't have a set. You don't have a name to call it. So that's a little bit of a tricky situation, and it's often said to be ghosts of big things. This set A, we will show it later on. We will show it that this set A, in NBG way, if we say it, this is a set which is not a small set. This is a large set. So this question doesn't come up at all. I cannot have this question. I cannot have this thing. So we will see that this is a large set and this can never come up. So this is taken out. Yeah. So you cannot have a large. So that's why I use the word small. Now, the first thing is that, as you said, Xander, you could do up to 15 and then from 16. So this statement says, so when I write more than one, so it means So negation of small xy will mean that, yeah, as I have written, small xy will be small, x is a small set and y is a small set. Okay. And then this says if x and y are not small sets, then this will be empty, this will be empty, and this will be empty. Yeah. Okay, we will see to it, but before that, anything to ask in this section 2.1, where I list the first 4 axioms.
I had raised issues with axiom 2 in this.
Yes, I'll come to you. I'll come to your issue, Malatse. Others, Xander, Brad, Eric, Ben. Any issues? Okay. There are quite a bit of issues. Firstly, let's look into extensionality. Xander, can you tell me what it means?
They are equal sets. When you work with 2 equal sets.
Yes. But why does it have to be an axiom? I know if things are equal, then if u belongs to x, then you must also belong to y. If you go to exercise 2.2.1, the equation 11, is that not all about equality? Now, this is exactly stated in this remark 2.2.3. What I wanted to say is, the notion of equality is not taken, not assumed, not even understood in set theory. There is only one predicate which belongs to. Okay? And equality of sets is therefore defined by, it gets defined by this action. Do you see the purpose therefore? So, keeping in mind my intuition that, okay, if I am to consider a set as a bundle or as a class or a collection of things, then I must consider them to be equal if they have the same things. Right? This is intuitively correct. Yeah? Is it right?
Yeah.
But I don't know what is equal. You see the problem. If you now think, my words x equals to y is not a well-formed formula in my dictionary, because the only predicate symbol that is there is what belongs to. Right? So how the hell do we say? And therefore this axiom of extensionality now comes into being. It therefore says how should it is. So now you see, we all agreed that is right, that should be taken, but that cannot be actually framed even in our language. And therefore the axiom of it is required, it's an axiom, so we have to assume this. So we define a relation called, written as x equals to y, and that's how it is defined. And then if you look into exercise 2.2.1, it says for every set X, the first one, X is equal to X. Sure. If I replace this X and Y by the same thing, obviously this statement is true for each U, and therefore by extensionality X is equal to Y. And you'll have to use the same argument to say B, C and D. Okay? So now if you read, so therefore with this definition of equality given by the axiom of extensionality, we come to these properties of equality. So it is not trivial. It is not trivial because we didn't know in theories that we start off or we do. We don't ask this question, equality. What is equality? I know X is equal to Y, or X is, I know that. Yes, you know it. And therefore, you in your subconscious use these four things. But here it is not known. Remember, known in set theory means it must be a well-formed formula of set theory. And well-formed formula of set theory, we have already known how to get hold of it. So X equals to Y by that token is not a known statement, not a known word. So I cannot make such statements. That's why this axiom of extensionality, and therefore we have to check that it really is what we know as equality. And that's actually exercise 2.2.1. Okay? So, read this 2.2.3. The equality of sets by axiom 1 is a defined relation between sets. Well, some other authors prefer to take it as a primitive predicate like belongs to, and in such case it would be there. They would assume the properties stated. But for us, since we have not, we must have that axiom of extensionality. Okay? Now for them who do take it as a primitive, they still have an axiom of extensionality. It is a kind, one side for them will become trivial. X equals to Y implies for all U this part will become trivial. So for them the axiom of extensionality is only this formula on the left hand side implies X equals to Y. So they are the axiom of extensionality for them who consider equality at the start, for them is a way of connecting these two unknown predicates. Okay? And for us, it is very important because we didn't start off with it. So it is a defined relation completely, and we have to check that it does what we want. Okay? So X must be equal to X. If X is equal to Y, then Y must be equal to X. So if X is equal to Y and Y is equal to Z, then X must be equal to Z. And what does the last one say? So suppose you have a well-formed formula, okay, and a variable X is free over there, and you want to replace that variable by another variable Y. Okay? So, now if you tell me that X was equal to Y, then the truth of that well-formed formula which you had with X should not differ, should be the same as when you replace that free variable X by Y, and so the truth of that must be the same. So that's exactly this second one. If X is equal to Y, then phi X. So this involves D actually involves running down this ways of building a formula from the atomic ones. So you have to run down that recursion kind of a thing to give a proof of D. Yeah. So you have to first show that suppose if you take an atomic formula phi x, then this is true. Now if it is true for phi x, it is true for negation. If it is true for phi and psi, if phi looks like, say, join of two things or and of two things or implication and so on, you have to show. So on. Okay? And then, so that's about it. I defined small over here, although I used it before. Okay. And then in the context, actually, I had no other place to put this small. I put it later on only. Okay. Now, that's about extensionality. Now for axiom for set building. Now, the way it is stated is not fully correct, and I obviously didn't state the fully correct thing because I wanted this this input from. Firstly, before I go over there, Malatse, see, in axiom of extensionality, well, it is a formula in where x and y are free variables, right? Does everyone agree? X and y are free variables, right? U is not. Okay? U is not, but x and y are free variables. Agreed?
Yes.
Okay. Now let's look into set building. It says, suppose you take x, which is free. So whenever I write phi x, I already said that x is a free variable in phi. And the statement, the formula phi, doesn't involve the set A. So the letter A never appears there. Now what do you mean by that? There exists a A such that x belongs to A. So what I am saying is, it's actually a very, very loose statement, and this statement actually cannot be made any more formal. It has to be understood in this scheme. So what is it saying? Think of all the possible sets that have not appeared in that expression, in that writing of that formula phi. Amidst all of them, what this axiom is saying, there exists a set A such that x is a member of A if and only if x is a small set and phi x is true. Okay? Alright? So it has to be understood in this way. So over here, this x, so here, although x is still a free variable, and you cannot in any way bound it, because you are trying to look for all those x's for which phi x is true. So all those small sets x for which phi x is true, and you're building your set out of, you're building your A out of this. Okay? And we shall henceforth write this A as this. So herein comes the set builder notation, and it is actually coming from this axiom for set building. Is this clear now? Malatse?
down as you do there. The thing is, my problem was that I had read that, for instance, when like set theory aside, but then when a statement you have that there exists what's this, a quantifier that exists, we usually cannot have an implication or by implication that follows, because of now it's not in the correct logical form, and we usually have ends if we have the logical quantifier that exists, and then the
Wait.
implications and by implications they usually go together with the for all.
No. You see, let's try to understand this. That's not true, because by implication is a logical connective, right? So it connects two statements, right? Now, look into this statement. One statement is X belongs to A.
Okay.
And the other statement is X is a small set and phi X is true. Phi X is true, right?
Okay, yes.
So, obviously, now small set X is a small set. This is obviously. So, if I write this down completely, well, if I expand this is actually an abbreviation. This is actually the formula that exists a Y such that X belongs to Y and phi X, right? Okay?
Yes.
Now, X belongs to Y is an atomic formula. So, this one is a perfectly valid, well-formed formula.
Yes.
And I have taken phi X to be a well-formed formula. So, this and phi X, this is a well-formed formula. Right?
Yes.
On the other hand, A belongs to X. This is an atomic well-formed formula. And I have said if I have any two formulae, or the other way around, X belongs to A. Any two formulae can be connected by these logical connectives. So this is also a well-formed formula, right?
Yes.
Now
Yes,
over here in this well-formed formula, both X and A are free variables, right?
Yes.
Now in this formula, X is the only free variable, but A is now bound. Okay? So it is not true that there exists A cannot come with a by implication or not, because it can. Yeah?
Okay.
Alright?
Okay.
Okay. Alright, I didn't see this objection, but I thought something else as I said. So now you see that this axiom for set building is a little bit off the line, in the sense that I need to say this first sentence. So phi X is a well-formed formula not involving the set A, and then I write this. So somebody may ask, what happens if it doesn't involve the set B? Well, as I said, So this statement has to be understood as this: for all the sets A, B, C, whatever, that have not appeared in phi x, the same statement is true. Okay, so what is this statement saying? Therefore, it is saying that for all these sets that have not appeared there, I can build a set A whose elements are precisely those sets which are small and for which phi is true, phi x is true. Clear? Okay? And then, so this statement also holds for this. I can write, so sorry. So I can write the same statement. So let me write it rather. So I can write this statement: A, x belongs to A if and only if small x and phi x. If B doesn't appear, then I can write the same statement: small x and phi x, and so on. So it is actually a whole scheme of such statements. So the axiom of set building is not a single set. It is a whole scheme of statement for each A that doesn't appear in the writing, in the expression for phi x. Clear? Okay?
Yes, I don't have a problem with it.
Okay, now here is the second utility of axiom of extensionality. If you just told me this, then I don't know how are these sets given, how is the set A given by this and this are related. Well, extensionality then comes in to say A is equal to B. Why? A is equal to B. Why? X belongs to A if and only if this happens, if and only if X belongs to B. So by extensionality. So this is with extensionality. So now you see how these two axioms therefore tell you that although this is a scheme of such things, any two such are equal, and therefore from here onwards, therefore I shall write this unique set in this way. Okay? So this therefore validates the formula and validates this writing, this symbol that A is equal to this. Yes, because these two statements together tell me that any two such sets are set. Okay? Clear? Everyone?
But what you're essentially saying is that it validates the curly bracket notation.
Yes.
If we're not naming our set A or naming our set B, if we don't give the set a name, it just validates the curly brace notation.
Yes.
A that says in front of A. It's just the name we choose.
It's just the name that we choose. Yes, and so therefore this set written on the right hand side uniquely represents a unique set given by this axiom for set building and axiom of extensionality, right?
Yes.
Yeah. So that's the whole idea then. Okay? Clear? So now you see how, okay, before I make any other ranking. The third axiom, what did you understand of this? Yes? Anyone? Brad? Any input?
The third one, is that the one, sorry, I don't have the thing in front of me, but is that the one where you can add them up? You can take two sets and put them together into a new set.
Yes, so the axiom of pairing,
Pairing.
what does it say? It says that for all x, so I'm writing it down, for all x, for all y, there exists a set. Yeah, there exists a set. Why is it vanishing? There exists a set A such that A is a small set and X is a member of A and Y is a member of A. Okay? Alright? So that's the axiom of pairing. So let me write down this. So this is the axiom of pairing. The axiom of Powershift and the axiom of union. So what does this say? For each set X, okay, let me so for each set X, I want to say that there exists a set B such that for all Y is a subset of X. First I want to say that B is a small set. And Y is a subset of X implies that Y belongs to B. I need to say something else also, sorry. I also need to say that okay. Now I have to be very, very careful. And the third one says, for all sets X, there exists a set B such that for all sets Y, you have and you want to make this small, and if you have a Y belongs to X, then you have Y to be a subset of B. Okay? Now, pairing is the simplest. What does it say? Well, it says that you take two sets, x and y. You will get hold of one set A, which is a small set, and it contains both x and y as elements. Okay? So now, coupled with your extension, therefore, or if you look into this, the moment you say that it is a small set and x is a element, so x and y both become small. All right? Okay? All right. Now you can make this formula. Let me write it here. You can make this formula phi xy. What is this formula? Z is equal to x or Z is equal to y. Okay. Now, if you have from our principle, see x and y over here, x and y are fixed, right? When I have taken this for fixed x and y, okay. Let me write it in this way. So first you fix your x and y, and then once you fix it, it is no more free because it is fixed. It's no more a variable. So now you have this. So z is a formula. Z is a free variable. So you can have this set. So what is the set? The set such that z is equal to x or z is equal to a. So it says that there exists a small set which contains them, and now with the axiom of extension you can therefore make up this set, which we will then call the pair. So this is the notation for this pair. It is called the unordered pair, and the notation for this is this, which comes from our axiom of extensionality and set building. So you see, all these are required. But let me give an understanding of axiom of union. What is this axiom of union? So what are you trying to do? Think of this x. What are you trying to do? Think of this x as a family of sets. So it is something like this. And this is the intuition behind it. So this collection, okay, so x, elements of x are each one of these circles, okay, these bags. What are you doing? For some such set, you want to get hold of a b such that firstly you are telling me that this set x is small. The thing that you are telling me is here, it is so whenever y you take from x, it means that y is a subset of b. So what is it that you are making b of? You are collecting all the things that were in this bag and in this bag and in this bag and in this bag, and that huge collection that you make of so you just empty out all these y's in a single place, and that is the b. So this b is going to give us, in the same way, it is going to give us this set, which is the union. So what is the union of x? Well, this contains of all y's such that there exists there exists a z. Let me write in this way. So this is the collection of all z such that there exists a y in x, such that z is a member of y. Okay? So it's the collection of all these z's such that it belongs to some one of the y's which was there in x. Yeah? And now if you try to look into this, what is this doing? This is syntactically, this is just the opposite. So what is this doing? It's taking x again, and then if you take a subset, so this is the picture now. So if you take a y which is a subset now, okay, then it is a member of B. So it is the collection. So here this B is kind of roughly the set of subsets. Okay, so that's the thing. Now that's the first picture, and then it says that, remember, it says that for a small set x and a small set, there exists a small set B which contains all its subsets. The same over here. For a small set x, there exists a small set B which contains all the elements of its elements. Right? All the elements of its elements. Yeah? So, the small x and small b is important. I don't know what will happen if they are not small. Okay? So, in this context, therefore, we can now provide these sets in 2.3. Okay? So, that's the context, therefore. If you look, so if you take instead of x 4 in 4, that's the unordered pair, as I said. The 3 is the, do you have this note open? Because I am referring to you, it will be better if you have it open on your site, on your side. Because I don't have to write it again, so that's why. Do you have it open?
Yes, 3 would be the unordered pair.
Yeah. 3 would be the unordered pair, but for when x and y are same. So that's the singleton, right?
Yes.
Then we have the ordered pair, and that's how we write it. That's the definition. Then we have what we will call the successor, and then union, as I said just now. So its union is what? It contains those elements which are elements of elements. So it contains this y, which is an element of an element of x. Okay, so that's the union. Intersection, well, this is the other one. So this is again a formula, so we can define it. So here, what is it? These are those these are those elements which are elements in all of them, the elements, right? Which are elements of each one of them. Okay. So that's the intersection. Obviously, this is the complement. Number 10 is the relative complement, the difference, and the Cartesian product. Okay. So we have all these sets in our hand. Now the exercise 2.3.1, coming to Xander's question. So now you see, I'll help you with one of them. So it says if small x, then, okay, let's see. So you have told me that x is not a small set. So that means x belongs to y. It never belongs to y for any y. Okay? See, x, I have fixed x, so I have this formula phi y. And axiom of extensionality plus set building tells me that I can have a set Z such that phi Z is true. That's fine. But what let's look into this. When shall I write this? I can write this. This means that so there exists a small set such that Z belongs to that. So Z is, firstly, this Z is small. So, and phi Z is true. Phi Z is true means Z equals to X. Okay, Z is small. But now you know, since Z is small, there exists a T, say, such that Z is a member of T. Since Z is equal to X, by extensionality, it is telling me, since Z is equal to X, I can replace this Z by X and still the formula would be true. So there exists a T such that X belongs to T. But this statement then says that X is small. But you have started with the saying fact that X is not small. So this statement cannot be true. What's the problem therefore? So therefore, negation of small x implies Z is not equal to X. So you cannot have this statement to be true. Okay? Since you cannot have this statement to be true, you cannot make this set. Alright? So therefore, this set, well, this doesn't exist, so this is just the empty set. The only way it can exist is the empty set. This being the empty set. Yeah? Okay? Now this was the full formal way. Another way is this. There is a little bit of a snag in this second part, second proof. What was the empty set? What was the empty set? The empty set was okay. So you can tell, so this is a false statement. Small z and z equals to x. This is a small statement. This is a false statement. And z not equals to z is a false statement. Both statements are false, so therefore this is equivalent. Okay? But what is this? This is actually telling me. So this is a false statement. And how do I write this? Well, the only way to write this is this, which is a bad way of writing, you will say. Yes, but it is this, and this side is fine. Okay? So, therefore, this false statement is bi-equivalent to z not equals to z. So, this statement is true. Therefore, from axiom of extensionality, this is equal to this. Clear? Clear? Any questions? You see, the initial parts to build up is difficult. But now if you see, well, you might think that there are 48 questions. Most of it should be simple. But the difficult ones will be up to 19. Okay? The rest is simple. You have to just produce the... so for instance, let's try this one. So here obviously your x is small, so you don't need to bother. So what is this? And what is this? But z equals to x is if and only if z, so therefore these two are same. Okay? So immediately you see 20 falls out. Similarly over here with this and so on. So you can carry on in the same way. I have done the simpler ones, but you should be able to do them. Okay. I expect lots of hiccups and lots of questions coming back from you. So I'm not telling all of it, but I want you to ask the questions. So yeah, now let you speak. You tell your inputs and queries and whatever. I'll stop you. Yes? Brad or anybody else, any questions, issues? I hear no one. Are you all asleep?
Not asleep, Doctor. I don't have any questions.
Is it going above the head? Too difficult.
Some of it's going above the head, other bits of it feel too easy, if you know what I mean. It's like what you just showed with the pairing X with itself. It's like you see us and you're like, that really, it is almost trivial. But then sometimes you're looking at a problem like that, just don't know where to begin.
Yeah. So you see, you must remember that this actually means a formula, and then you have to prove you only have these two axioms at your hand. Right?
Yeah.
Okay, and so what is this calculus about? You see this equation 20, which we just proved now, singleton x is equal to xx. So it immediately tells us that given the definition of sets as per axiom of extensionality and set building, till now what we have, only with these two, we can actually we can disregard whether we are considering whether we write a single element twice or thrice or n times or 1000 times. It doesn't matter, right? Because even if you write it once, it's there. So the whole question is, an element is there or not. If it is there, it is there. It doesn't make any difference if it is 100 times there or not. So, distinct elements, a collection of well-defined the distinctness is not required. It is immediate. The next one, 21 says, therefore, the order in which you write the elements doesn't matter. Yeah? Again, an element is there or not. It doesn't matter in what order you write it. Okay? Now, the 22 obviously tells us when xy will be equal to x prime, y prime. Yeah? 23 tells us when will xy be equal to the ordered pair xy. So, see the difference. 22 and 23, compare them. 22, well, x can be equal to x prime or it can be equal to y prime. So, it could be that x is equal to, so you have just, it could be that you have twisted it. But, so, xy, the set xy is equal to yx, the set yx, just written in 21. But the ordered pair xy is not equal to the ordered pair yx unless x and y are same. So, therefore, 23 gives us a way to kind of say, well, there is now, in this set, there is now a kind of a positional advantage, or the position has been taken into account. Two such things are same if and only if their corresponding coordinates or corresponding position things agree. Okay? So, this is the difference. That's why it is called an ordered pair and the previous one is called an unordered pair, because it doesn't matter. Right? Now, if you see union of xy of the unordered pair, well, what are you doing? Union of xy, I said union of a set. What union of x? What is it? It contains those elements which are elements of its elements. So, elements which are elements of either x or y. So, this must be it. Right? So, you just have to now run down that formula for union of this and intersection. So, union of pair xy, so that therefore justifies this formula actually. So, that's why this we shall henceforth write simply as this, as we write. Similarly, this we shall henceforth simply write as this. Okay? So, that's how we write it. And similarly, this is the 26 and 27 should be simple. And then 28 is also written. Now, if you see 29 says, if you look into the union or intersection of the singleton x, well, what is it? Union of singleton x. It contains of all those elements which were members of its elements. But it had only one element, which is x. So, it contains all the members of x. So, it must be this. But now, if you see, union of the pair xy is obviously x or y. Intersection of the pair xy is xy. So, now you have an algorithm to get hold of the first coordinate and the second coordinate. How do you get hold of the first coordinate of a pair? You take its intersection. That gives you the first coordinate. How do you get hold of the second coordinate? You take the union and take the difference. That's it. So 31 and 32 give you ways to select the first. So now therefore, see, these are the things that are coming up. You have now created this ordered pair and now you want to say, how will you say that this is the first coordinate? Not by looking, you must tell me a formula. That must be the first coordinate, that must be a formula. Right? So, the formula, so now this is a singleton. How would you get hold of this? So you see, you told me union of x is x, and this is same as intersection of x. You told me union of xy is xy. Intersection of xy is x. So, union of xy minus the intersection of xy, this is y. So, how do you get hold of x from here? This is the root. So, what is your first coordinate? Your first coordinate is intersection of xy. What is your second coordinate? Well, it is the intersection of union of xy minus intersection of xy. You might think this is weird. What the hell? I could see and look at it and say, but well, yes, you could look at it, but was that a well-formed formula? Now you have a well-formed formula to express the fact that x is the first coordinate of xy. And that is this. Yeah? Until and unless you have a well-formed formula, you cannot use that. So that you must have this embedded from right now on, that whatever we have done so far in set theory, was it a well-formed formula? Can I write it completely in terms of things that I have defined previously, or just can it be, forget about the length of the statement. It will be big, but still a finite thing coming out of those atomic ones. So you are going to make and, or, negation, implication, whatever. From that atomic statement, can you write it down? The moment you tell me this, see, the axiom of extensionality tells me that I can write 2.3, if you see number 8, Roman 8, it gives me a well-formed formula for intersection of x. So it gives me an formula for this, and therefore intersection of that is also given by that, and so on. So I can write a well-formed formula for that. Okay? So that's the whole idea, that I can. What do you mean by capturing all of mathematics in terms of sets? That means each one of the things that we are speaking about must be expressed in terms of sets and sets alone. So for instance, the statement x is the first coordinate of xy. This also has to be represented as a well-formed formula, or in other words, as a set. So the first coordinate of xy is intersection of xy, of the ordered pair xy. Second coordinate, intersection of the difference of union and intersection of xy. So that's it. I'm not saying you have to remember all of this. We will forget. But this is the starting point. This is how we are building our algebra of sets. Yeah. So you see, This should therefore tell you why we are doing this. This is not just not I wanted to take 96 hours from your time going through all of this and proving them simple things. You see the reason. You see why I am doing it. The reason is it must become a well-formed formula. And so all the things about algebra of sets that we have done have been encoded over here. Okay? Now comes this 2.3.3, which is still a problematic one. And we will see this until the next batch of our axioms come. We will see this defect. And with that I will stop. And now, Xander, what do you say? Yeah? Do you see now that although things look very trivial on the surface, I'm not saying they are difficult, but there needs to be some computation and before we can ascertain this. Do you see this? I mean to say, do you see the necessity of this computation? Yeah? Yes? Your input. Anyone?
Okay, Doctor. If I may ask, then just to clarify if I'm getting what is said in the note and also in the lecture.
Mm-hmm.
Okay. I had read some things on formal languages or first order logic. Now, your remark on 2.2.3, is it the same or is it saying what is usually said with some authors who write saying that, for instance, all formal languages, or let me say it like this. So first order logic is a class of languages that share a certain logic that we build upon. And then they only differ by their functional symbols or the predicates. Okay? And then now, your remark on 2.2.3, is it saying that equality, for instance, we take as a predicate in our logic?
Yes.
In a logic sense.
Yes.
And now, what we're trying to prove in exercise 2.2.1, we're lifting the logic onto now what we are talking about, which is sets.
Yes. Yes. There are two approaches. So people do take in equality as a predicate. Okay? And when they do so, they are going to take A, B, C, D of 2.2.1 as the properties of that predicate. Okay?
Yes.
So that's one approach. You can start your logic by that. What we are doing is, we are not going to take that equality in our theory. So we are starting off, we are saying we don't need equality. We would define it by extensionality, and then once we define it, we need to see that it is really the equality that we actually think of. So that means we have to prove these A, B, C, D of 2.2.1. Right?
Okay, yes.
Yeah. So, yes, there are two ways, two different ways. Some people might assume equality. So we say a logic with equality, or we say a logic without equality. So here it means that we have taken a logic, we have started off with a logic which doesn't involve equality. So without equality means it doesn't involve equality, but we are putting in equality as a defined symbol. It is defined in terms of our belongs to. Okay?
Okay.
Yeah. So that's the purpose of extensionality. Others? Eric, you have been conspicuously quiet.
I have nothing to say, Doctor.
Why? Is it getting all abstruse nonsense? Or what is it?
No, I'll try to work through the problems and then I'll see how far I can go with them. Where I'm having challenges, I'll see, communicate with you.
Okay. Okay. So that's what I had to say today. Xander, Brad, Ben, if you want to add something more.
All good.
Same. All good. Thank you, Doctor.
Okay. Brad?
I'm okay, thanks.
Okay. So I expect well, as I said, bombarding now from you like Putin. So there will be several questions while you start answering them. I expect bombarding and I will reply back. You can obviously engage between yourselves within the Telegram group or whatever. Eric, I didn't see you in the Telegram group.
I haven't yet installed the application in my laptop, but I'll do it.
Yeah.
Sorry, Doctor. Eric, you don't necessarily have to download it. You can use the online version as well. You can just create an account, if I'm correct, and then you can use it. I've posted the link again in the chat box.
No, it's okay, thanks.
Very good.
Okay. So there can be discussion going on in the Telegram group, and if you want me to answer it, you can directly ask the question to me there also. I'll also answer there. And if I find it is difficult, I'll write an email. So that's how we will communicate. But I expect questions. So with that, shall we stop today?
Okay. Thanks very much, Doctor.
Thank you.
Take care. Cheers, everyone.
Cheers. Keep well.
Thank you, Doctor. Enjoy
Thank
your
you.
evening.